In the last video, we arrived at the probability density function of the 1D Maxwellian distribution. We said that the probability density of the 1D Maxwellian distribution was given by probability density function was given by a e to the power minus alpha Vx squared. We also stated that due to isotropicity of the motion, all the three directions of the molecule of the perfectly ideal gaseous molecule was exactly the same. Thus, they must exactly have the same probability density function. They obey the same probability density function of speeds. Probability density function of speeds. We had also begun a discussion on the 2D Maxwellian distribution, the famous 2D Maxwellian distribution, wherein the idea was that the two directions of velocity of the perfectly ideal gaseous molecule were independent of each other, and the net probability to get a molecule lying in the range Vx with x component of velocity in the range Vx plus dVx and Vy to Vy plus dVy. So these were the x component, ranges of the x component and the y component, could be obtained just by multiplying the individual probabilities along the x and y direction. So we obtained that our dn xy by n as a squared f Vx squared into Vy squared dVx times dVy. Now we have stated previously that what was the value of this Fvx squared and Fvy squared. So we may put the values directly. This is alpha Vx squared plus Vy squared. This is just simply what we have obtained. Now this, as we know that Vx squared and Vy squared are nothing but the components of the velocity in the 2D plane. Now if we remember our discussion of the coordinate system that we did for a very brief amount of time, that this was a coordinate system, a rectangular or the Cartesian coordinate system. This was the Vy axis, this is the Vx axis, and our velocity was somewhat like this. This was our velocity. This is our velocity vector. The velocity vector was thus this, or let's not call it V to avoid confusion. Let us call this as C1. This C1 was related to V1, Vx and Vy as C1x squared plus Vx squared plus Vy squared. This is the resultant of the two perpendicular velocity components Vx and Vy, where C1 was the magnitude of the velocity, and this is what we see here. So this is what we see here. So this we will replace Vx squared plus Vy squared as C1 squared dVx into dVy. What is the second task that was at hand was actually that we had now a probability density function for this was actually our probability density function for the 2D Maxwellian. But the problem was that this is indeed the functional form of the probability density function, but with this dVx into dVy was not in terms of the net velocity c1. So we have to bring this dVx into dVy in terms of c1, and before we do that we must understand what is this dVx into dVy. This dVx into dVy, like we did, was that if we moved some small distance dVx along the x-axis and dVy along the y-axis, and we let's go. Okay, so if we had the okay, let's do it again. We had dvx along the x-axis, so let's call this distance dvx. Let's call the distance, let this be O origin AB, and let this be CD, and let's go ahead along the y-axis. Let's call this dvy, and let's call this as E, and so this was our dvy, this is our dvx, and we can call these 2 points right here as GH. Let's isolate this rectangle dvx into dvy. This is CD, this is rectangle CDGH. The rectangle CDGH has a has one dimension as dvx and one dimension as dvy. Clearly, this dvx dvy, the area of this rectangle is actually equal to, of this rectangle CDGH was actually equal to dvx into dvy, and this was actually called the, this is called the area element. What is the significance of this area element? Was that what this area element is somewhat important once we defined something in our last video called the point density. The point density was defined as the number of molecules that were present, that was traveling in this speed range within that number of molecules per this area element. The point density was nothing but the number of molecules that were present in the gas molecule which per this area element. This area element actually was, this point density actually was the density of all the velocity vectors that were lying between the range, that had lying between the range C1 to C1 plus dC1. Since we defined the problem as from Vx to dvx, Vx plus dvx, and Vy to Vy plus dvy, and this was now a two-dimensional problem, we can translate this easily to a problem of C1 to C1 plus dC1. This was interesting, and now we had actually converted two velocities into one resultant velocity C1 to C1 plus dC1. This was the point density, equation of point density. The point density actually we had arrived in our last video, that this was actually equal to n square, not n square, but this was n a square. Actually this point density can be arrived from equally from here, that this was n into a square e to the power minus alpha c1 squared. So this point density was the number of velocity vectors that lay in this small rectangular region, right? And not even in this, this was actually the velocity density of all the velocity vectors present in the overall distribution, as the distribution was said to be uniformly dense. So this was our idea of point density. Now what happens is, if we want to find out the total number of molecules in the distribution, total number of molecules with speed C1 to C1 plus dC1, what do we have to do? Remember that C1 is a speed. and let's call this as dn, and this dn, what do you think this will be equal to? Remember that I said that this dv, this was actually the point density, was the density of all the velocity vectors lying in the range c1 to c1 plus dc1. So this is some density. So, and this was a density per area. So if we multiply this density by an area, which was the area of that rectangular region, rectangular GFDH, right, rectangle CDGH, right, we could get back our number of molecules that were lying in the range C1 to C1 plus DC1. This was simple, but this, what will be this area? What will this area be? Will this area be the area of a single rectangular box or not? Right? Now, again, let us go back to our picture of coordinate system. This was our coordinate system, Vy. Or let us now draw the four quadrant coordinate system, the complete full coordinate system. What if I told you, what is the can you draw all the velocity vectors in this coordinate system that had the speed c1? You'd say that okay, this is a velocity vector having speed c1. We ascertained it. But okay, someone else will say that we have thought of this velocity vector having c1. This was another velocity vector with speed c1. Someone will say there is another velocity vector somewhere else. My point is that whenever there is a speed c1, there can be infinite directions that can be attributed to it. And what is important to us now is what is the locus of all those points which had a magnitude c1. Locus of all those velocity vectors. What is the not vectors maybe? What is the velocity of so all those? What was the locus of all those points which were at a distance c1 from the origin? What do I mean by that? What we were looking for is all the vectors that had a magnitude c1, means that they have a distance c1 from the origin. So what I was looking for was a velocity locus of all those points having a distance c1 from the origin. If you know that we had followed the equation of Vx squared plus Vy squared equal to c1 squared. This was Vy, this was Vx. So now can you tell me what is the locus? Yes, it's that of a circle, and that too a circle of radius c1. So let's draw a circle of radius c1. This was a circle of, let's say, radius c1. This circle had a radius c1, and if we move a distance dc1 out from the surface of this circle, from the perimeter of this circle, we have a region dc1. But obviously, since now this has become an infinite, we have infinite number of vectors, this will be lined up, this perimeter of this circle will be lined up by infinite such surface area elements, and these area elements would make up make two concentric circles from the center of the circle, from the center for the origin, and the origin and one circle would have a radius c1, while the other circle would have a radius c1 plus dc1. So c1 plus dc1 and c1. Now what is the region of this ring? What is the area? What would be the area of this ring? And this is our required, this area. This is the area that we required. And this area of the ring was actually given by pi c1 plus dc1 whole squared minus pi c1 squared. So this came out to be pi c1 squared plus pi dc1 squared plus 2 pi c1 dc1. Our basic geometry, we are applying basic geometry and algebra, and we will cancel off our pi c1 squares, and we are left with 2 pi c1 dc1 plus pi dc1 whole square. Now dc1 was an infinitesimal quantity which was anyway very close to 0. We square it, it goes more close to 0, so we can make it, we can consider it 0, we can neglect its effect, and this was 2 pi c1 dc1. We had the dn, or let's use small n. Now let us revert back to capital N, because this is basically a dn that we had defined, dn c1 rather, that we can define as the number of number of molecules that have speed lying in the range c1 to c1 plus dc1, and we had the point density into area. What was our point density? Point density was n a squared e to the power minus alpha c1 squared into 2 pi c1 dc1, and we have the equation as dn c1 by n a square e to the power minus alpha c1 squared dc1. So this is or we have missed out our 2 pi c1. There's a 2 pi c1. So we have arrived here, and we can compare it to our original equation, and that we see that this dvx dvy has been completely replaced by we see that the dvx dvy was completely replaced by 2 pi c1 dc1. Now what the another task that remains at hand is the determination of this a and alpha. What is this a? This a is actually a normalization coefficient. Remember that what we are dealing with, so the idea of normalization is what we are dealing with are probabilities, and when you integrate the probability, so in this case our probability was dnc1 by n. The integration of dnc1 by n implies that we are summing up the values of the probability. The probabilities, and this integration when done over all the space, that is all the space, all the range of velocities, in this case all the range of speeds that the molecule is allowed to take, if we integrate over all that, this should equal to 1. This is our idea of probability, and the constant a must actually be chosen likewise. So if we have a normalized idea of normalization, we should be able to see that this integration should be from c1 equal to 0 to c1 equal to infinity. Why? Because c1 0 and c1 infinity are the range of the values of the speed that the molecule was able to take. Speed cannot be negative, so we have to take it between 0 and infinity. c1 equal to 0, c1 equal to infinity. This is, and we put back our functions. A squared, this was our a squared e to the power minus alpha c1 squared, and we have 2 pi c1 dc1, and this should equal 1. If we take out our constants from this equation, this was a squared 2 pi in 0 to infinity, this was c1 e to the power minus alpha c1 squared dc1, that was equal to 1. So this is our equation. If we multiply divide by 2 alpha, we have a squared pi by alpha. Since the 2's are cancelling out, we have 0 to infinity 2 alpha c1 e to the power minus alpha c1 square dc1. The step, so we have multiplied and divided by 2 alpha. The reason being, we are using a simple idea of the derivative, that e to the power minus alpha c1 squared, we have to we are using a simple class 12 calculus integration knowledge, that we have to take alpha c1 squared as a t, and the variable alpha c1 squared dc1 was actually equated to dt, and we had the idea like this, that a squared pi upon alpha is equal to we had integration 0 to infinity, and we had alpha c1 squared as t and 2 alpha c1 as dt. So we had this 2 alpha c1 dc1 can be replaced by dt. So we have dt here, and we have e to the power minus t equal to 1. So e squared pi upon alpha 0 to infinity. So the integration gave us the result e to the power minus t by minus 1 from 0 to infinity. That's exponent e to the power minus t. So this should be e to the power minus t, but divided by the derivative of the minus derivative of minus t, that was minus 1, and we will take the minus as common, and pi by alpha e to the power minus t 0 to infinity equal to 1. This was a squared minus pi upon alpha, and we have here e to the power minus infinity minus 0 e to the power 0 equal to 1. E to the power minus infinity was actually 1 by e to the power infinity, and 1 by e to the power infinity means 1 by e to the power a very large number, that would tend to 0, and this became minus a squared pi upon alpha. This was 0 minus 1. We don't forget the negative sign, and this is a squared is equal to alpha by pi. So we have the value of a squared, which is exactly what we need. So when we write the density function, let's first write the distribution in terms of dn c1 by dn. We had a square sum, we started an a square here, alpha by pi 2 pi c1 into e to the power minus alpha c1 squared, and there was a dc1, and this was actually our density function, the probability density function f c. Let's call this function as fc1 squared, and this is actually a density function for the 2D probability density function for the 2D distribution. Let's write fc1 as, not let it fc1 squared as alpha by pi, not squared, let's write fc1 for now, and this actually became alpha by pi into 2 pi. Let's not cancel for now for c1 square. So now the problem was this alpha appears in our equation, and alpha appears here as well and here as well, and the next step is exactly going to be that the determination of alpha, which we should do in our next video.